Hello, my name is John Cody. In this video, we'll be doing it's part 2 of our series on alternate forms for the quadria of a projective quadrangle in universal hyperbolic geometry. So in the first video, part 1, I looked at an alternate form for this equation, and we're going to explore some more alternate forms for the equation based on triangulations of a projective quadrangle. Okay, so I covered all of this material in the previous video, so have a look at that. In part 1, what this is all referring to, but essentially it's about geometry. There being two sides of geometry, and affine geometry and projective geometry, and it takes the point of view that geometry is really about formulas. Okay, so in the previous video I looked at this formulas for this triangulation of a projective quadrangle, projective points A1, A2, A3, A4, and we had chords between projective points A1 and A3, and between another chord between A2 and A4, and they intersected at this point A5, and there was a quadrant S between these two projective lines. And in this video, I'll be looking at the case where there is the extra point is in general position rather than the intersection of two chords. So we're going to be looking at this triangulation here of a projective quadrangle and coming up with formulas for that alternate form of the quadria of the projective quadrangle. Okay, so this fifth point, it's point A5, not labeled, but this could be anywhere inside this projective quadrangle. Okay, so what's new with this projective quadrangle is that the spreads between these lines is no longer just one value S. It's going to be a different spread for each projective triangle. So there's spreads U1, U2, U3, and U4, but all the rest is the same. Okay, so we're going to be applying the spread law to each of these triangles. So for projective triangle A1, A2, A5, the spread law is given in this first set of equations here. It's Q1 divided by U1 is equal to P2, quadrants P2 divided by spread T1, P2 divided by T1, and that's equal to P1 divided by R2, quadrants P1 divided by spread R2. For projective triangle A2, A3, A5, the spread law is given by these equations. Quadrants Q2 divided by spread U2 is equal to the quadrants P2 divided by R3. There's P2 divided by R3, and that's equal to P3, quadrants P3 divided by T2, P3 divided by T2. The next set of equations here is for triangle A3, A4, A5, and that's Q3, quadrants Q3 divided by spread U3 is equal to quadrants P3 divided by spread R4, P3 over R4, and that's equal to quadrants P4 divided by spread T3, P4 over T3. So the spread law gives that for the third triangle, and finally the fourth triangle, A1, A4, A5, it's Q4, quadrants Q4 divided by spread U4 is equal to quadrants P4 divided by spread R1, and that's equal to quadrants P1 divided by spread T4. Okay, and we're doing something similar to last time. We're going to be looking at this quadratic equation for the quadria of a projective quadrangle, which was given in a previous video, or explored previous video, improved in the previous video. And this quantity Q1, Q2, Q3, Q4 is, using the spread law, we're going to be, for each of these set of equations, we're going to be bringing the spread in the denominator here up to the other two sides, so we'll just be left with Q1 on the left-hand side. And we're going to do the same thing with the other equations. We're going to bring U2 up, and we'll just be left with Q2. For this equation, we're going to bring U3 up to both sides and just be left with Q3 on the left-hand side. And similar with this equation, we're going to bring U4 up into the numerator on both of these equations and just be left with Q4 on the left-hand side. And then we're going to multiply Q1 times Q2 times Q3 times Q4 all together, and we'll get, using different combinations of these terms on the right-hand side, we get U1 times U2 times U3 times U4 times P1 times P2 times P3 times P4, all divided by R1 times R2 R3 times R4. And we can also get, by using a different combinations with the T1s in the denominator here, or the T's in the denominator, we get U1 times U2 times U3 times U4 times P1 times P2 times P3 times P4, all of that divided by T1 times T2 times T3 times T4. And that's also equal to, when we take in the numerator the P2 terms and the P4 terms in the numerator, and then multiply the Q1, Q2, Q3, Q4 all together, we get this equation on the right-hand side. That's equal to U1 times U2 times U3 times U4 times P2 squared times P4 squared, all divided by T1 times R3 times R1 times T3. And lastly, we also get, when we use the terms P1 in the numerator and P3 in the numerator here for these two. When we multiply Q1, Q2, Q3, Q4, we get, that's equal to U1 times U2 times U3 times U4 times P1 squared times P3 squared divided by T2 times R4 times R2 times T4. And we're going to do the same thing as we did the last time. We're going to multiply the Q1, Q2, Q3, Q4 by a clever choice of 1, which is 4 times 1 minus S1 times 4 times 1 minus S3, all divided by 4 times 1 minus S1 times 4 times 1 minus S3 in the denominator. And when we do that and combine it with this third equation here, we're going to get Q1, Q2, Q3, Q4 is equal to U1 times U2 times U3 times U4 times P2 squared times P4 squared divided by 4 times R1 times T1 divided by 4 times R3 times T3 times 4 times 1 minus S1 times 4 times 1 minus S1 in the numerator divided by 1 minus S1 times 1 minus S1 in the denominator. So all we do is take this value of 1 here and multiply it by that equation up here and to get this right-hand side, equation 2. And again, we're going to apply the alternate form of the triple quad formula in universal hyperbolic geometry, which said that a plus b minus c all squared is equal to 4 times a times b times 1 minus c. And when we do that, we get R1 plus T1 minus S1 squared, this left-hand side here, is equal to the right-hand side, 4 times R1 times T1 times 1 minus S1. And then we're going to do it again. We're going to get R3 plus T3 minus S3 squared is equal to 4 times R3 times T3 times 1 minus S3. So that's R3 times T3 times 1 minus S3. So we're going to substitute this into equation 2 in the denominator. We're going to replace the denominator with this piece on the left-hand side. And then we get, for equation 2, we get Q1 times Q2 times Q3 times Q4 is equal to 16 times U1 times U2 times U3 times U4 times P2 squared times P4 squared times 1 minus S1 times 1 minus S3, all divided by R1 plus T1 minus S1 squared times R3 plus T3 minus S3 squared. That's equation 3. And lastly, we're gonna substitute equation 3 for the Q1, Q2, Q3, Q4 into equation 1. So here's equation 1 up here, which is our original quadratic equation for the quadria of a projective quadrangle. And we're going to substitute this Q1, Q2, Q3, Q4 with equation 3. And we get A is the quadria of a projective quadrangle minus Q1 times Q2 times S2 minus Q3 times Q4 minus S4, all of that squared is equal to 64 times U1 times U2 times U3 times U4 times P2 squared times P4 squared times 1 minus S1 squared times 1 minus S3 squared. All that divided by R1 plus T1 minus S1 squared times R3 plus T3 minus S3 squared. So that's equation 4. And using similar reasoning with the triangulation, the other triangulation of the projective quadrangle, and okay, so we're going to be, for this Q1, Q2, Q3, Q4, we're going to be using this last term here with a P1 and P3 squared in the numerator. And when we apply similar reasoning, we end up with this equation, equation 5, which is A minus Q1 times Q4 minus S1 minus Q2 times Q3 minus S3 all squared is equal to 64 times U1 times U2 times U3 times U4 times P1 squared times P3 squared times 1 minus S2 squared times 1 minus S4 squared, all of that divided by R2 plus T2 minus S2 squared times R4 plus T4 minus S4 squared. So equations 4 and 5 are two quadratic equations in A. And you'll recall in a previous video we used the quadratic compatibility theorem to determine the common solution of a pair of compatible quadratic equations to get the equation for the quadria of a projective quadrangle. So here we are in Universal Hyperbolic Geometry. We have a projective quadrangle A1, A2, A3, A4. This is the null circle. The blue circle is the null circle, and the quantity A for the projective quadrangle is represented here. We have quadrances, side quadrances Q1, Q2, Q3, Q4, and spreads S1, S2, S3, S4. And we had these two quadratic equations. And these two quadratic equations turned out to be compatible, meaning they had a common solution for A. And when we applied the quadratic compatibility theorem, which is theorem 1 in the book Divine Proportions, Rational Trigonometry to Universal Geometry, when we applied that formula for the common solution, we got this expression here for A. And you'll notice there is no square roots in this equation because that's what the quadratic compatibility theorem gave us. So if we do the same thing now with our equations 4 and 5, equations 4 and 5 are compatible quadratic equations, and we're going to apply the quadratic compatibility theorem to them. Then we get this expression for the quadria of a projective quadrangle. This is like the alternate form. So this equation here also gives us the quadria of a projective quadrangle when we apply the quadratic compatibility theorem to equations 4 and equation 5, which we derived previously. Okay, so these are another alternate forms for the quadria of a projective quadrangle when with a triangulation with an internal point in a projective quadrangle in an internal point in general position inside the projective quadrangle. Okay, so thank you for listening, and I'll provide some links to some videos for references. And also in the description, I'll provide some links